All right, let's see what we have here. In the last section, we learned inverse functions of algebraic equations. And the steps to find it. Switch X and Y. So here's step one. And then step two, solve for Y. This Y will become your inverse. So X minus B over M equals the inverse of Y. Okay, that's just the mechanics of it. So how does an inverse function work? In a regular function, we're given X, we solve for Y. That correlates to the inverse function of Yx. So basically, what you're looking for is what X value will give me the solution Y. That's what we're looking at. So let's begin with the trig functions. So find the inverse of sine. It helps if we first draw the function of sine. Pi over 2, pi, 3 pi over 2, 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. The bounds are from -1 to 1. So the sine function at 0, sine is 0. At pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's -1. Just remember, if we look at this thing, 0 is over here. Pi over 2 is here. Pi is there. 3 pi over 2. And remember, the sine values deal with the y values. So at 0, sine is 0. At pi over 2, sine is 1. At pi, sine is 0. At 3 pi over 2, it's -1. And then all the way around to 2 pi, it's back to 1, or back to 0. If we go backwards, from sine going backwards will give us at negative pi over 2, which be -1. At pi, it's 0. At negative 3 pi over 2, it's back up to 1. And at negative 2 pi, it's back to 0. So the sine function looks like this. The amplitude is 1, because it goes from 0 to up 1, 0, -1. The period where it begins to repeat itself is 2 pi. Now, what's the inverse? What's the opposite of sine? It would be 1 over sine, which would be cosecant of x. That's the inverse. I'm sorry. I'm getting ahead of myself. So the inverse of sine, don't worry about that. The inverse of sine. Remember, now we switch the x and y's. So here, our points of our graph are going to be y, x. So in other words, everywhere we have an y-x intercept, that becomes an asymptote. It's a vertical asymptote. Whereas here we're looking for the y values when that. So since we're looking for the inverse function, we know that it's going to be the opposite of this. So here's the inverse function. Start with the vertex. And if it's below the x-axis, you go down. If the vertex is above the x-axis, from that point, you go up. And that's the cosecant function. I'm trying to get myself mixed up again. So this is the inverse. This is the reciprocal. So as we see, I'm sorry, redraw this graph. So for the inverse function, and the regular function for sine, the domain is from negative infinity to positive infinity. And the range is from -1 to +1. Because our domain goes left and right, highest we can go, lowest we can go is -1. But for the inverse function, we have to switch these. The domain will be negative or -1 to +1, and the range will be negative infinity to positive infinity. Yeah, because it has to fit within our x's and y's. So the x's here are now the y's there. So the range is from negative infinity to positive infinity, and it goes from +1 to -1. Same with the cosine function. If the domain of the cosine function is from negative infinity to positive infinity, that means that's the range, the vertical aspect of it. The range of the original function, which from -1 to 1, is the domain of the inverse. All right, so of course the domain, So our domain now for the inverse function can only go from -1 to +1. This is the y, this is the x. So it's stuck between here, and it goes on forever. The shift. The next function is the tangent function. The tangent function, since tangent is the slope, is sine over cosine, it's the y over x. What the tangent function looks at now is we have vertical asymptotes everywhere that cosine is equal to 0. So it's pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2. So anywhere cosine 0, cosine is 0 at pi over 2, at 3 pi over 2. No, cosine is 0, yeah, pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. It's 0 anywhere sine is 0. Sine is 0 at 0, at pi, at 2 pi, negative pi, negative 2 pi. It's an increasing function. So this is what the tangent function looks like. The domain is between negative pi over 2 to pi over 2, because that's where the first interval is, and it repeats itself from there. The range is from negative infinity to positive infinity. So therefore, the inverse function of tangent the range, actually the domain is the x value. That one is from negative infinity to positive infinity, and the range is between negative pi over 2 and pi over 2. So let's see what that graph looks like. So the domain, it goes left and right from negative infinity to positive infinity. And the range is from negative pi over 2 to pi over 2. Cosine or sine is 0 at the origin. It's got to stay within these bounds. So it looks like this. So we take the tangent function and rotate it 90 degrees and flip it since it's the inverse. So we know it goes from negative infinity to positive infinity, check. Crosses at 0, check. But since it's an increasing function, it starts as we go left or right, it starts low, ends up high. The cotangent function, its inverse is the inverse of cotangent. The domain, cotangent is 1 over tangent, which is the flip of tangent, which is cosine over sine. So we have to see where our vertices are. So anywhere sine is 0, That's an asymptote. Remember, sine deals with the y values. It's 0 here and it's 0 here. So it's 0 at 0, it's 0 at pi, and it's 0 at 2 pi. Those are asymptotes because the bottom is 0 at those points. Cosine is 0. Cosine of 0 is at pi over 2 and 3 pi over 2. So at pi over 2 and 3 pi over 2, negative pi over 2, those are the intercepts. Now, when are cosine and sine the same? Cosine and sine at pi over 4, sine and cosine are the same. So at pi over 4, this is pi over 4, it's 1, that one. So we see here is that it's a decreasing function. So the domain of the cotangent function is between 0 and pi. The range is from negative infinity to positive infinity. It's parentheses. It goes up and down forever, which means that the inverse function its domain will be between negative infinity and positive infinity, and its range will be between 0 and pi. Can't be sure because that's going to be the bottom part. So its graph so the function cotangent, we got that. Now, so we know our domain is negative infinity, positive infinity, and the range has to go from 0 to pi. So this is now pi to negative pi. So the horizontal domain is that. Since it's a decreasing function, it crosses at pi over 2. That's our function. It's a curve. It goes like this. That matches our inverse function. And the last two, we have the secant function and its inverse is the inverse of the secant function. We have to know the new domains and the ranges here. So secant is 1 over cosine. So we first look at the cosine function. And from -1 to 1. So where is cosine 0? Cosine 0 at pi over 2, at 3 pi over 2, negative pi over 2, negative 3 pi over 2. The easiest way to do the secant function is if we first draw the cosine function, if we first draw that, Since it's a reciprocal function, the secant graph starts from the vertex, and if it's above the x-axis, it goes up. If it's below the x-axis, it goes down. If it's above the x-axis, it goes up. It starts, and they share the same vertice. So that's the inverse function. Which means now for our inverse, because for our domain for the secant function, we're going from let's see, our domain here is between negative pi over 2, pi over 2. So that's where the asymptotes are. And the range is from 1 to infinity. 1 to infinity. Or it's also, or it can go down, so it's negative infinity to negative 1. And that one is from pi over 2 to 3 pi over 2. So if it's in the first interval, it's positive. It's in the second interval, it's a negative. And that translates over here to the inverse function. So remember, to make this thing look easier, remember now we take the x values, those become my y values. This is pi over 2, this is negative pi over 2, pi, negative pi, and so on and so forth. And my x values, those are the old y values. So it's 1, 2, negative 1, negative 2. So for the first one, when x is 0, or when x is pi over 2, it's an asymptote, so it can't go there. So we're going from, our graph will look like, when is equal to 1? It's equal to 1 at 0. But I can't really use that because I can't have 0 in there. It's 1 over 1 is 1. So where is it? Positive 1? When y is 0 at positive 1. And it's bounded by pi over 2. So it goes like this. And the negative side, it's going from 1 to there. So it's going from at 1 and here, that's the asymptote. Because we're looking at both of these. It's decreasing here and it's increasing there. So that's our graph of our inverse secant function. So the domain of this one is x is less than equal to our negative infinity to negative 1, or 1 to infinity. And its range is from 0 to pi over 2 and from pi over 2 to pi. So it's practically 0 to pi over 2 or pi over 2 to pi, because it all depends on which side you're on. And the cosecant is the same as this one, except it's flipped. is pretty much just take this part, move it down here, move this part, or this part here goes up there. So let me draw that. -6. The function is cosecant. The domain, the range. Cosecant is 1 over sine. So we look at the sine function and reciprocate it. So pi over 2 pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. So where's sine, since we have a rational expression, where is sine equal to 0? At 0, at pi, at 2 pi, negative pi. So our domain is between 0 and pi over 2. Or asymptotes. And the range is from well, it's now for the negative side, we're going from negative pi over 2 to 0. If it's on the negative side, we draw the sine function. So the secant function, or cosecant function, looks like this. It starts from the vertex and it goes the opposite direction. So the domain is from 0 to pi, 0 to pi, and the range is from 1 to infinity. Or if it's from negative pi to 0, the range is from negative infinity to negative 1, because we're down here. So the inverse function will be bounded by pi over 2, negative pi over 2, because that's where they're going to be zeros. That's where we're going to start off from. And our y values are 1, 2, 3, 4. So the inverse function at pi over 2 starts off at 1. Then it decreases. So the domain is from 1 to infinity, and the range is from 0 to pi over 2. And on the other side, on the negative side, starts off at negative pi over 2, but it has to be bounded by pi over 2, negative pi over 2. So that's that graph. Inverse trig functions. Also called arc functions. What does that mean? So if I have y is equal to inverse tangent, that's the same thing as saying the arc tangent. So they're arc functions. and goes through all of them. So whatever function you have, this negative is replaced by the arc symbol. All right, let's look at example 1. Let's see how this stuff works. Remember, the hardest part about inverse trig functions is you have to think backwards. Because if I ask you sine of pi over 2, then you would say that the sine of pi over 2, since it's on the very top, is 1. Then the inverse sine of 1 is equal to pi over 2. So here's the x, gives me the y. I give you the y. What x? What, in other words, you're asking yourself, what x value gives me this y value? That's how the inverse functions work. We're trying to find the inverse tan function of this picture. This is pi over 6. Remember, on pi over 6, the value of this point is 1, 2. Because it goes up 1 unit and it goes over 2 units. So the inverse tangent of pi over 6 is equal to, what's the hypotenuse? Remember, tangent is equal to sine over cosine. What is sine? Sine is the y value over the hypotenuse. Cosine is the x value over the hypotenuse. So in order to solve this, we have to find the hypotenuse. Okay, this right here is important. If you don't remember how sine and cosine are related to these pictures here, these images, think of SOHCAHTOA. So if we start here, our angle is pi over 6. Sine of the angle is opposite over hypotenuse. Opposite of this angle. So the opposite of this angle is 1. And the hypotenuse we're going to figure out is radical 3. So the hypotenuse is radical 3. Cosine is adjacent over hypotenuse. So the adjacent of this angle is 2 over radical 3. And tangent is sine over cosine, which is opposite over adjacent. Because if we did these, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Take the top fraction, multiply by the reciprocal of the bottom. We have opposite over adjacent. So from this angle, the opposite is 1. The adjacent is 2. is 1/2. So what this says, what this equation here says, the tangent at pi over 6 is equal to 1/2. Therefore, the inverse tangent of the y value of 1/2 is pi over 6. So the hardest part about using these is you have to think backwards. Let's take another one. We're going to do the same angle, pi over 6. But this time, our hypotenuse will be 2. Our height will be 1. That means our base is radical 3. So we find the tangent of pi over 6. Remember, tangent is opposite over adjacent. Opposite is 1 over radical 3. So therefore, the inverse of 1 over radical 3 is pi over 6. Whereas inverses and regular functions are simply just change this x and y values. But there are 2 values that we can find for the inverse function. This is the first one. The first one we found was inverse tangent of 1 over radical 3 is equal to pi over 6. Now, the other side we think about is in the fourth quadrant. Why? Because the tangent function is symmetric about the x-axis. So the other one but remember, we're doing x and y. So now this is 2, this is 1. But now here, this is our x value. Now this is our y value, and that's our x value. For this other one, we have to switch it. So in the other one, so it was 1 here. Now it's the value for x. The x value here used to be radical 3, so that's my y value. Because now, if I switch x and y values, I have the point radical 3, 1. That's that point of that line right there. So I go over here now to 1 radical 3. I took the x, I switched x and y, I could find the inverse tangent of this one. So this function is equivalent to the trig function tangent of x is opposite. From this angle, opposite is radical 3 over adjacent, which is 1. So it's just radical 3. but it's negative because it's in the fourth quadrant. Now, instead of pi over 6, here, because we've changed those, it's pi over 3. Now, why do we use that? Because remember when we did in trigonometry, you have 3 angles that you always look at. One of them is 30 degrees. One of them is 45, but that's where sine and cosine are equal. They're both square root of 2 over 2. And then we have at 60 degrees. And that's what we did here. Here, let's say we had 30 degrees. Now since we changed the x and y values, we're now going to 60 degrees. So these are the two values that we're looking at. Because we switched the x and y, we changed it here to y and x. All right, so we'll do the tangent function first. So the tangent function of negative radical 3 is equal to pi over 3. Since we're doing this one here, this is 60 degrees, which is negative pi over 3. This is 60 degrees, which is pi over 3. This is pi over 4, and this is pi over 6, which is what we're doing. When we did this one, that's at pi over 6. Now we're doing this one, that's at negative pi over 3, which is this one down here. And that's our inverse function, because the tangent of pi over 3, the tangent of pi over 3 is square root is 60 degrees. Or in this case, in our case, it's negative radical 3 over 1, which is negative radical 3. So now that we have the trig function, we can look at the inverse function. So we'll take the negative of the answer, put in the inverse function, and that'll give you the angle that came from. So in other words, what this says is there are always two answers for any trig functions because of the periodicity. Let's look at the derivatives. Of inverse trig functions. So let's look at the derivative of the inverse of sine. Well, here we know the derivative. We know the derivative of sine is cosine. That's what we've been doing all along. Now, how's this going to relate to our trig functions? So we have to look at where's theorem 3. Remember, the theorem 3 says the derivative of an inverse function is always going to be the derivative of the function time of the derivative of the inverse function. That was theorem 3 we did last section. We do the same thing here. So the derivative of the inverse function. The inverse function is the inverse of sine. We have the original function of sine x. We need the derivative of our function, f prime. The derivative of sine is cosine, which we did that already. So the derivative of our inverse will be 1 f prime. So f prime is cosine. And what goes inside there is our inverse function, which is sine inverse of x. Okay, yeah, that looks nice, but we're not done. Because we have to get them into the same terms as a function of x. We need to rewrite this as a function of just x, no trig functions. So with this part here we're looking at here, so the cosine of the inverse of sine since this is a function within a function, we use substitution. So this is cosine of u. Now, using the trig identities, remember, the trig identities are cosine squared plus sine squared equals 1. 1 plus tangent squared equals secant squared. And then cotangent squared plus 1 equals cosecant squared. These are the trig identities. It comes from the Pythagorean theorem. Cosine squared plus sine squared, if you think about it, it's the unit circle. X squared plus y squared equals r squared. Since we have a unit circle, everything's between 1 and -1. So our radius, so r is equal to 1. So we have x squared plus y squared equals 1. X deals with cosine functions, so it's cosine squared x. Y deals with the sine functions. So there you have our first identity, the Pythagorean theorem, in trigonometric form. If we divide each term by cosine squared, cosine squared divided by cosine squared is 1. Sine squared divided by cosine squared is tangent squared. 1 divided by cosine squared is secant squared. There's a second trig identity. Now, if we go back to the original and we divide everybody by sine squared, cosine squared divided by sine squared is cotangent squared. Sine squared divided by sine squared is 1. 1 divided by sine squared is cosecant squared. So that's how we found 3 identities. Since we have cosine u, we can use cosine squared plus sine squared equals 1. Cosine squared is 1 minus sine squared. Cosine is the square root of 1 minus sine squared. So cosine squared can be rewritten as this, as a square root of 1 minus sine squared u. Okay, so let's expand that. We have 1 minus sine squared u. This is u. Inverse sine squared. Now, the reason we needed to do that is because the sine of the inverse of sine of x is equal to x. The tangent of the inverse of tangent of x is equal. So the trig function of its inverse, they cancel each other out. So we're just left with the argument. So this now can be written as 1 minus x squared, since this equals x. So the inverse of the derivative equals 1 over 1 minus x squared. Which gives us to our formula. Formula 1. The derivative of the inverse sine function of x squared, or x, make it u, it could be anything we want it to be, is equal to 1 minus u squared times the derivative of u, where the absolute value of u has to be less than 1. Because normally, why is this? Because normally the sine function is greater than 1, but now since we're doing the inverse, we switch x and y, so we change the direction of it. So there's our formula 1 with our sine function. So let's say our function was the inverse of x squared. Find the derivative. So the derivative of this function is the derivative of the inverse function of u, du dx. So u is equal to x squared. Because of our trig identities, what does sine equal? Cosine squared plus sine squared equals 1. So sine squared is 1 minus cosine squared. Sine is 1 minus cosine squared. So we have, according to this, we have 1 over square root of 1 minus u squared times the derivative of u. Du is 2x. So 1 times 2x is 2x. 1 minus U is x squared, so we have x squared squared, which gives us 2x, 1 minus x to the fourth. That's the derivative of the inverse. All right, so let's look at the other trig functions. Let's derive those derivatives. What if we have the inverse of tangent? Remember, theorem 3 gives us this. We have to use that. All right, so our f of x original function is tangent. The inverse of that function is the inverse of tangent at x. And the derivative, the derivative of tangent is secant squared. We did that earlier. So according to this, the derivative of our inverse, f prime is secant squared, f inverse is tangent Okay, so what do we do with this? Remember, in order for us to cancel these out, they have to be the same value. So what exactly is secant squared? Because that's inverse tangent, we can't touch that. So what's secant? Remember, cosine squared plus sine squared equals 1. We divide by cosine squared, we get 1 plus tangent squared equals secant squared, right there. So secant squared is 1 plus tangent squared of our x. Our x was inverse tangent, x. So tangent squared is 1 plus tangent squared x. This is our x. So we have 1 over 1 plus tangent squared tangent inverse of x. So it's 1 plus, so tangent x times tangent inverse of x is equal to x. And it's squared, so it's x squared. And that is our derivative. This is of the tangent function. So the derivative of our inverse tangent is equal to this. 1 plus u squared times du dx. That's our formula. So whenever you're taking derivatives of tangent functions, you use that. So we've looked at so far the derivative of sine, derivative inverse of sine, the derivative of the inverse of tangent. The cosine is going to be the same as a sine one, just going to have a minus in there. How about the secant? So if y equals, we'll find the derivative of this function. So what do we know? Since this is an inverse, remember, inverses, if x and y, its inverse is yx. So if I took the secant of both sides, let's just play with x right now because I don't worry about doing the du dx later on. So the secant of y, these two cancel, so it equals x. So now we take the derivative of both sides. The derivative of secant is 1 over cosine. So we'd have to use the reciprocal function, the quotient rule for 1 over cosine, which would give us sine over cosine squared, which is sine over cosine 1 over cosine, which is tangent times secant. So the derivative of secant is secant tangent. So the derivative of this side is secant y tangent y dy dx, but we're taking with respect to x. The derivative of x is 1, so the derivative is 1 over secant y tangent y. But we're not done. We want secant and tangent in terms of x, because now they're in terms of y. So we have secant y is equal to x, and tangent y is equal to, because we want tangent in terms of secant. So using our identities, we have cosine squared plus sine squared equals 1. Divide everything by 1 over tangent squared secant squared. So tangent squared. So tangent is equal to plus or minus secant squared minus 1. So tangent y is the same thing as plus or minus as secant squared y minus 1. Secant y is equal to x. So this is equal to plus or minus secant y is x. So it's x squared minus 1 because of this. So now we can take both of these and put them in place of there. So the dy dx now becomes secant y is x, tangent y is plus or minus square root of x squared minus 1. And there's a derivative of that. Can the value ever equal negative? Yeah, if x is negative, the whole thing's negative. If x is positive, the whole thing's positive. So, yeah. So it can be positive or negative. Okay, so that's what we started off with. So we have here, so our rule is d secant inverse of x over dx is equal to, instead of putting plus or minus, we'll just put absolute value of x. You'll see most of the formula. So this is your formula we're dealing with. That's with x. If x is a function, so what is it with secant, inverse secant of u? If inverse secant of u, then the derivative of that would equal 1 over the absolute value of u squared minus 1 times du dx. If u equals a function of x. So my function, inverse function is inverse of secant, arc secant, 5x to the fourth. The derivative. So using this, so we have d dx of inverse secant of 5x to the fourth, where this is u, is equal to 1 absolute value of 5x to the fourth square root of 5x to the fourth squared minus 1 times the derivative. Since u is equal to 5x to the fourth, the derivative is 20x cubed. Five is a constant, it'll never be negative. X to the fourth is always, in this example, x to the fourth can never be negative, so we don't need the absolute values. So we have 20x cubed over 5x to the fourth. 5 squared is 25. Power to a power you multiply, so it's x to the eighth. 5 goes into 24 times. Cancel 3 of them, so we have 4 over x times the square root of 25x to the eighth minus 1. That's the derivative. This should be cofunctions. Inverse function of the inverse cofunction. Identities. So the cofunction of x, or the inverse of x, is the same thing as pi over 2 minus the inverse of sine. This is very similar to sine and cosine to begin with. Remember, cosine goes to 1 and like this. That's cosine. The sine function looks like this. This is cosine, this is sine. So sine and cosine are nothing more than cosine x equals sine x minus pi over 2. Or you could say pi over 2 minus sine x, it'll shift it to the left. So that's what this is saying. It works the same with cofunctions. The inverse cotangent. Since that's the inverse of cotangent is pi over 2 with sine and cosine. You can say the derivatives of them. So the opposite of sine and cosine, opposite of cotangent is tangent. So here's the cofunction. What cofunction simply means is it's similar to, it's the same answer. It's as that other function. Whereas cosine x would get the same answer if I did this. That's why they're cofunctions by this, because they give you the same answer if I put the same x value in there. The inverse or the arc cosecant is pi over 2, and the opposite of cosecant is secant. And those are its cofunctions. So as an example, what if we had cosine of arc cosine of x? Find the derivative of that. So what we're looking for so we can rewrite cosine, the inverse cosine, as pi over 2 minus sine inverse of x using identity. So we just rewrote that. Okay, so this is the difference rule. So we have the derivative with respect to x of pi over 2 minus the derivative of sine inverse of x over dx. This is a constant, so the derivative is 0. So what we're looking for is the negative of the inverse sine function. And as we did that earlier, we did this one earlier. So the answer is 1 over square root of 1 minus u squared. So it all goes back to what we did earlier. So that equals negative 1 over square root of 1 minus x squared. That's the derivative. So in summary, the derivative of the inverse of sine is equal to 1 over the square root of 1 minus u squared times du dx, where the absolute value of u is negative. The derivative of the arc cosine of u with respect to x is equal to the negative of the similar function, 1 minus u squared du dx, where the absolute value of u is less than 1. So the only difference between the sine and arc, cosine, sine derivatives are the signs. The derivative of the arctangent, 1 over 1 plus u squared times du dx. The derivative of the arc secant of u is equal to 1 over the absolute value of u times u squared minus 1 du dx, where the absolute value of u is greater than 1 now. Because remember, it's less than 1 for the sine and cosine. That means for the secant and cosecant, because they're reciprocal functions, they're going to be greater than. Ooh, I haven't done cotangent. The derivative of cotangent inverse. It's the same as this, but it's the negative of it. So in the last one, since we did sine, cosine, tangent, cotangent, secant, this is going to be cosecant. The cosecant and secant are opposite, so that one's positive, this one's going to be negative. 1 over absolute value of u squared minus 1 du dx. And the absolute value of u is greater than 1. So what this summary tells us is, instead of going through and trying to derive everything, because we saw how we derive it using theorem 3, it's just mechanical. You just jump straight to these. If you're asked to find one of these, just use these formulas. Whatever your u value is, that's all you have to pretty much factor out. All right. That does it. That is the end of section and the end of chapter. Any questions? All right, everybody. I will see you guys on Wednesday. Have a good day.